Hello students, welcome to series of lectures on digital speech processing. So in this video you will be able to learn MEL frequency substral coefficient, okay? So which is most widely used method for extracting the feature extraction from speech signal. So that we can see in this video. So let's get started. So this is the lecture learning outcome. On completion of this lecture you will be able to estimate the feature extraction of speech using MFCC. Alright, so this we have already seen in the previous video. So the feature or parameter extraction can be possible either frequency domain parameters or time domain parameters you can use, or time frequency domain. But these two things which are not there in our syllabus, and we'll be sticking to the frequency domain parameters, the two. So this filter bank analysis is already done and we left with the MFCC. So that we can see today. Okay, so what is MFCC and why MFCC? What is delta MFCC, delta to delta MFCC, everything that we can see in this video. Alright, so this also we clearly see in the previous video. What is a MEL filter band? So even though uniform and the non-uniform filter bands which are not suitable for the human ear, so rather than the spectrum should be flattened, now we need to consider the triangular spectrums, and which is log frequency scale actually, and which are very suitable for the human ear. Okay, that is what we are generating the feature extraction from the MFCCs. Alright, so MEL frequency substral coefficient. So I already told MFCC is the most used parameters in the speech technology development. MFCC computed from the speech signal using the following three steps. So first, compute the FFT power spectrum of the speech signal, apply a MEL space filter bank to the power spectrum to get the energies, and compute discrete cosine transform of the logarithmic filter bank energies to get the uncorrelated MFCs. Okay, so we need to compute the DCT. I told you there are several ways actually we need to focus on to the transformation technique, but especially in the feature extraction, that too in the MEL frequency substral coefficient. So we are going to be using the DCT. I will tell you why DCT we are using in this. So computing the MFCC, here we have the flowchart which is given. Waveform is there, and then DFT. So log amplitude spectrum. MEL scaling is there, discrete cosine transform, and there we will be getting the MEL frequency substral coefficient. So this is the flowchart actually you need to understand for computing the MEL frequency substral coefficient. Okay. So this is we clearly mentioned in the previous analysis also. In the substral domain we clearly seen. So from the speech signal we will be getting waveform, and then that speech signal, that is an acoustic, we can call this an acoustic waveform, that can be converted into the another domain with the help of the DFT, and then log amplitude spectrum, and then MEL scaling that we need to do, and here DCT we are going to be providing. Okay. Alright, so MEL frequency substral coefficients. So now what you need to understand here is that, so this is a scale actually, MEL scale we can call. So MEL scale from all the frequencies which is, so from 0 to 10,000 hertz scale. Okay. So now this we are going to be taken into consideration. Whatever the speech signal you may consider, that you are applying to the DFT, you will be getting the frequency spectrum. And then here that speech signal is multiplied with this MEL scale. Okay. So normally we will be having the triangular bands. Okay, so triangular bands, and this is the way how we need to convert. So normally, so these MELs will be converted, equals to 1127 when the frequency is given, for instance. Okay, so in what way this MEL scale is suitable, I already told you, because the human ear can persist only in the range of the log frequency scale, that is best suitable for the MFCC. Now, when I give the frequency, you will be getting MELs equal to 1127 logarithmic of 1 plus f by 700 to the base e. So this is the way how we are going to be converting. Okay. Now, so I already told you this MEL spectrum actually is kappa of L, that we have already seen in the previous slide, and you will be getting the discrete Fourier transform. So S of k is nothing but the speech signal. This is multiplied with the MEL frequency spectrum. Okay, so these two are going to be multiplying, and we'll get the whole range of frequencies, but only L sample that can provide. And this is the Lth filter from the filter bank. Okay, so where k is nothing but kfs by n hertz, and where L is varying from 0, 1 and so on up to L minus 1. So the total number of triangular Mel wedge filtering is 20. Okay. So this is a standard expression you can remember like this. Okay. The only thing is that we are multiplying the original spectrum with the Mel spectrum. That's all. So this is a Mel filtering band. So this is a time domain signal that's acoustic in nature, and when you apply the DFT method and you'll be getting the spectrum. So x of n is converting into x of k, and these are the several band pass filters you'll be getting. This is the first band pass filter, this is the second one, and up to how many number of band pass you can employ. So in this case, what you need to understand, so this is the spectrum actually. Now this spectrum is multiplied, okay, with the Mel band. So this is a triangular band actually we are going to be considering, and we are summing up all the features, and we are going to be taking the one feature extraction that from the each and every signal when you do. So these many features we are going to be extracting. So that is a way actually the thing that we are evaluating the process of features from the speech signal in this way. Now, what is a block diagram of Mel frequency substrate coefficient? The block diagram of extracting a sequence is consisting of 39 dimensional MFCC feature vectors. Okay, so 39 MFCC feature vectors. So this is the basic signal processing block. Much discussion is not required. Speech signal you have given to the pre-emphasis, and then window technique you are going to be applying, and then here the short segmentation of the speech you will be getting, and this short segmentation of the speech will be applied to the DFT, and you will be getting in the another frequency domain. Now this is the Mel filtering bank in the triangular structure like this, and when you apply the logarithmic, okay, and that's the logarithmic of that, and when you apply the IDFT, you will be getting the many coefficients, but among the coefficients we are only concentrating on the 12 MFCC coefficients. Okay, so assume that is frame 1, frame 2, frame 3, and so many frames you have divided. So from each frame, the 12 coefficients you are going to be considering from each frame. Okay, so here also is right. So this is the way how we are going to be taken into consideration of the coefficients from the MFCC. Okay, so when you take the speech signal, and the speech signal is divided into several frames, that is frame 1. So let me explain here so that you can easily understand. This is frame 2 and this is frame 3. And when you take the frame 1 separately, and you are going to be taking the 12 MFCC coefficient, that is M1, M2 and up to M13. Okay, and similarly for frame 2 and similarly for frame 3 also. Okay, so these many coefficients. Now 12 MFCC coefficients, and when you apply delta, this delta is nothing but difference between frame 2 to frame 1. Okay, again you will be getting the 12 delta MFCCs. Okay, so please understand here. The first way, straight away we are taking the 12 coefficients from the each frame, that's the 12 MFCC coefficient that you will be getting, and then we are taking the 12 delta MFCCs in such a way that it is a difference of F2 minus F1. Okay, so let us assume F2 has M1, M2 and so on up to M13. F1 is also have some other MFCCs, you know, MFCC coefficients. So you are going to be taking the difference, and again you will be getting the 12 delta. Okay, so 12 MFCCs and 12 delta MFCCs, and double delta nothing but this F3 minus F2 we are taking minus F2 minus F1. So this is the process actually we need to consider. Okay, so when you take the first derivative is nothing but, you know, velocity, and the second derivative nothing but an acceleration. Okay, so what you need to understand, how the format is varying, that is nothing but the velocity. Okay, how format of a speech signal is varying, that we are calling as a velocity. How fast the format is varying is nothing but an acceleration, that is nothing but double delta. So where delta is a velocity, how format is varying, so again we are taking the 12 delta MFCC coefficients, and how fast the format is varying nothing but double delta. We are taking the difference of difference, F2 minus F3 by minus F2 minus F1 like that. Okay, and again 12 delta MFCC. So from here we will be getting 36 coefficients, and the remaining 3 coefficients is nothing but coming from the energy. Okay, because you are going to be calculating the energies also, right? Okay, so directly one energy feature, and when you apply single delta, you'll be getting another, and if you apply double delta, you'll be getting 3. So total 36 plus 3, 39 coefficients you are taken into consideration from the MFCCs. Okay, that is what. So traditionally, first we need to consider the 12 to 13 coefficients. So first coefficients give most information. That is exactly example, Forman, spectral envelope, and everything that we are taking into consideration from the 12. And use delta and double delta MFCCs total 39 coefficients per frame. That is what I have explained clearly in the previous slide. This is what you can easily understand. Okay, so the spectrum is multiplied with the Mel frequency. So this is the Mel frequency spectrum. Right, so this is the DCT actually, Mel's spectrum, the logarithmic and then DCT. So why DCT? So the signal is real with the mirror symmetry. You can apply any kind of the transformation, but in this case, particularly we are taking into consideration of the DCT only, because the DCT is more efficient computationally. Okay, so the IFFT requires complex arithmetic, whereas DSCT is not. The DCT implements the same function as the FFT more efficiently by taking advantage of the redundancy in the real signal. So these are the things actually we should follow for DCT. Thank you, student. Thank you for watching this video.